Apply Kirchhoff's loop rule to single loop circuits, as mentioned in the figure, page 148. The diagram shows a circuit with two EMF devices and two resistors. The circuit has no junctions and only one loop. The same current flows. If point A is chosen to be the starting point, assuming that the direction of the current is counterclockwise, this is the direction of the current. This is R1. Just make sure that they're clear. This is VMF 2, and this is VMF 1. And assuming that the direction of the current is counterclockwise, we apply Kirchhoff's loop rule. So let's apply the Kirchhoff's loop rule counterclockwise as well and see what we will get. So we're going to move across the circuit counterclockwise, just like the current, starting from point A. So I'm going to start from point A. You can see that I'm entering the battery from the negative side and exiting from the positive. So I'm going to substitute this voltage as positive. So VMF 1. Here I'm moving with the direction of the current, so minus IR1. With the direction of the current as well, so minus IR2. Entering the second battery from the positive terminal, so minus VMF 2. Went back to the same point, I put the equal 0. So the sum of voltages across the closed loop is equal to 0. If the direction of movement was assumed to be counterclockwise, if the direction of movement was assumed to be counterclockwise and we apply the KVL, what's going to happen? So now we're going to move across the circuit counterclockwise, starting from point A. First, I go through the VMF2 from the positive terminal, so I'm going to substitute it as positive. I'm going through R2 against the current, so it's plus IR2. Similarly, I'm going through R1 against the direction of the current, so I'm going to add the voltage of R1, sorry. And then here I'm moving through the battery from the positive terminal, so it's minus VMF 1. We return to the same point we started from, so I put the equal and the 0. Notice that the direction of the assigned current does not affect the result. So if you apply KVL with the direction of the current or opposite to the direction of the current, if you move the circuit clockwise or counterclockwise, it's the same. It's going to give you the same values at the end. What is the current flowing through the loop shown in the figure? So you can see here there is no direction for the current, so I can assume one. Let's put the point at which I'm going to start moving from this point right here. And you can see that there is no direction for the current, so I'm going to assume direction according to basic knowledge of circuits. This voltage source is 6 volts, this is 3. I know, I can imagine the batteries as water pumps. This water pump is stronger than this one, so the water starts to move like this. This is the direction of the current. Of course, if you assume the direction of the current opposite, nothing will happen. It's just going to give you the negative sign at the end. Don't worry, it's just it means that the actual current is flowing opposite to your assumption, so there's no big deal. Let's say this is the direction of the current. Let's say I'm going to move through the circuit in the same direction as the current. I'm going to move counterclockwise and apply KVL. Starting from point A, you can see that I'm entering the first resistance in the same direction as the current. So the current's moving like this, and I'm moving with the direction of the current as well. So I'm going to substitute its voltage as negative. So minus I times R1 Because this is a single loop, the current is the same everywhere, so I'm going to call it I. Then you can see that I'm entering the battery from the negative terminal, so I'm going to substitute its voltage as positive. I'm entering the battery from its positive terminal, so I'm going to substitute its voltage as negative. I'm entering this resistance from the positive, the same direction as the current, so we're going to substitute its voltage as negative. So minus I R2 equals to 0. I return to the same point. Now R1 and R2 are 1 and 2 respectively, so let's put their values. 1 I times 1, so it's minus 1I. And R2 here is 2 ohms, so I'm just going to substitute its value, which is 2. So minus 1 plus 6 minus 3 minus 2, I gives you 0. Minus 1 minus 2, that's a minus 3I. 6 minus 3, that's plus 3, equals to 0. Throw this on the other side, becomes negative. Now if you assume to the direction of the current was opposite, if you assumed it will be clockwise, then you'll find that the current has a negative value at the end. That means that your assumption of the direction of flow of current is just opposite to what it really is. So if you assumed it to be clockwise, you'll get a negative here, and you'll know that it's actually moving counterclockwise. But here, because we assumed the right direction for the current is positive. So divided by negative 3 divided by negative 3 gives you a current of 1 ampere. So it is 1 ampere flowing counterclockwise.